Hello, Woodstock students. This is Mr. Brennan, and I want to spend a little bit of time discussing the idea of bond energies and how, in a variety of ways, we can use bond energies to figure out if a reaction is going to warm or perhaps cool the surroundings that they are that the reaction takes place in. We're going to start here with a very simple reaction, if you will, or a breakdown of a molecule, and show you a quick example of what we mean. On the left-hand side here, you see the hydrogen molecule. Hydrogen is one of 7 diatomic molecules that comes um, in pairs, and you can see here that the 2 hydrogens have a single proton, they each have a single electron, and they share it for some chemistry reasons that we don't have to get into right now. But H2 is its natural state, and if you wanted to pull them apart, uh, you might need some energy to pull apart those hydrogen atoms from one another to create 2 individual hydrogen atoms separated. Okay, so we go from H2 bonded pairs of hydrogen to 2H, 2 single hydrogen atoms existing on their own. Now, um, chemists, biologists, scientists in general have spent a lot of time looking at a variety of reactions, and each particular bond, like the one shared here between hydrogen, each particular bond has a certain known energy necessary to overcome the attraction between the 2 partners in the bond. And they put them in a table. And all we need to do in this particular case to sort of figure out like what's necessary um, is we need to figure out what the bond energy is in H2. How much energy is essentially needs to be overcome here. So here's an example of just such a table. Um, you can see that the columns are labeled bond and then kilojoules times inverse moles. That is the same as kilojoules per mole, and we don't need to bother too much about the units, but I hope you can hear that joules or kilojoules is a kind of energy, and I will just share for the moment that it turns out to be convenient uh, to describe that per mole, which is just a number of bonds, like a dozen is 12, a mole is a giant number of sort of um, chemical quantities or molecular quantities, atomic quantities, and so on. Um, Nevertheless, whatever, as long as you understand that this represents the energy associated with a certain bond and that the units are consistent, we can use this table to identify the amount of energy needed to overcome a bond. Um, and so here we have OH, which you would want if you were breaking up water, and OO as a single bond right here and OO as a double bond right there. Looks like there's more energy for double bond than a single bond. And also before we finish looking, and we can see down here the number for hydrogen, the HH bond is 435. We can see here that there's this word enthalpy, and this is just the word used to describe the molar bond energy. Okay, so this is the what sometimes is called the heat of formation and so forth. There's a lot of different names to it. I don't want to get hung up on the vocab, but that is what the this is referred to as an enthalpy, a certain amount of energy that's stored in a bond or released by a bond forming and so on. Anyway, you'll see that word come up, but I just want you to think about the energy that needs to be overcome when breaking up a bond. If we look at hydrogen here, the HH bond, okay, the number here is 435. So let's go back to the other slide and take a look at what it said there. You can see in this slide it says 436 kilojoules times inverse moles. Okay, and that number doesn't quite agree with our table. Our table said 435, but that is not uncommon in this realm. These experimental values for the bond energies are very difficult to measure, and so there's some disagreement as you go from source to source. So nevertheless, we have something in the realm of 435 kilojoules per mole, 435 units of energy needed to kind of break the bond here. Well, let's apply this now to a more kind of common reaction. This is just breaking apart a single atom, but you know atoms can be broken apart in a chemical reaction and then put back together. And the question becomes, has does that reaction need energy to occur, or does it release energy into the environment? So let's take a look at the combustion of methane. CH4 is methane, and combustion means we're going to combine or expose it to oxygen, and there'll be a chemical reaction between oxygen and methane that will produce CO2 and water and some energy. So we already have a hint that this should be producing some excess energy and should be warming the environment. But let's take a closer look at it, okay? First of all, you may notice that there are 4 hydrogens over here and only 2 hydrogens over there. So this is not a balanced chemical reaction. I'm just going to show you quickly how to balance it. Okay, if you add a 2 in front of each of these, the water and the O2, that will balance out everything. 2 times H2 will give you 4 H's. It'll also give 2 oxygens here along with 2 oxygens from the CO2 to give you 4 oxygens. And there's a single carbon on both sides. So that's what it looks like from a sort of written out point of view. But it turns out to be much more helpful to look at these molecules from a sort of a almost architectural point of view. So let's take a look at what methane looks like. Okay, methane is a family of hydrocarbons. Okay, it's part of a family of hydrocarbons, and like butane, it's the simplest hydrocarbon in that it's got a single carbon. Carbon wants to make 4 um, bonds. Hydrogen wants to make 1, and so spatially, this is what methane looks like as a molecule. So you can see here, we're going to need to think about CH as a bond, and that's going to happen 4 different times. We're going to break up those 4 bonds and then see how they reform with the CO2 in the water. So here's a picture of the methane, as we said, and then over here is sort of just a simple diagram of the O2 showing its double bond. Okay, so O2 has a double bond, and I want you to use that idea whenever you're dealing with like combustion. Okay, O2 comes in that style, and of course there's 2 of them because that's what we've got. So if we just focus on what's on the reactant side of the equation, we have a single CH4 molecule, 2 O2 molecules, and what bonds must we break? Well, as we said, there are 4 CH bonds, okay? And so whatever the cost of a CH bond is, we're going to spend it times 4. And then there's 2 double bonds of oxygen, and we need to look up on the table what those values are. But before we spend any time looking at the actual numbers, I just hope that you're feeling good about the fact that there are 4 of these, 2 of those, and we can look up those values on our table. Let's take a look at the product side and see how much energy is released. Well, we do essentially the same kind of calculation. We take a look at a single CO2 molecule, and the CO2 has a carbon in the center and then 2 double bonds to oxygen. okay? And H2O, which has an oxygen and single bonds off to the hydrogens. So we can do the same kind of calculation here. Now we have two of these CO uh, double bonds we need to reform, and four of these OH bonds to each in each of the two water molecules. Here's the bizarre thing, though. If it takes energy to break these apart, then when these pieces come together, when the products come together, they actually release energy, and they release the exact same amount of energy that's required to break those particular bonds. So we can use the same table to look up energy released or given back from the bonds that are forming. Now that may take a little bit of thinking to get comfortable with, but I do want you to appreciate the idea that if it takes energy to overcome bonds, then it seems pretty natural that when bonds are made, they must return energy back into the surroundings. Do the calculation, we can go to our tables and find that the CH bonds have an average value of 414 units. There are four of them, so we're going to spend 1,656 units of energy breaking up the methane. And we also have two double bonds of oxygen. Each one costs 502 units of energy for a total of 1,004. So to completely break down everything on the left-hand side, on the reactant side, we'll need a total of 2,660 kilojoules per mole. That's these two numbers added together. If we then take a look at the energy given back from the bonds that are forming, we've got two CO double bonds that are worth 730 units of energy, four OH bonds, which are worth 464 units of energy. The total of those two is 3,316 kilojoules per mole, which of course is significantly more than the amount of energy needed to take apart the ingredients. So the products release more energy than are needed to break down the um, uh, the, the reactants. And so when this reaction occurs, there'll be a release of 656 kilojoules per mole. And we can go back then to our original equation and show our original chemical equation and show that the energy released would be 656 kilojoules per mole of reactants that we use up. So we've just seen that methane is indeed an energy producing molecule, a molecule that when combusted will release a certain amount of energy, typically in the form of heat and light. As long as you have decent pictures of the structure of any given molecule, you should be able to run the same kind of analysis by using your tables to find out the bond energies. And you should be able to, say, look at butane and look at ethane and propane and so forth to figure out how much energy those uh, particular molecules would give up. Okay, these are all typical fuels that we might use. All right, so soon you'll be asked to look at molecules like this and use the tables to establish the energy spent on the reactants and the energy released by the products, and make a determination of whether or not the surroundings will be gaining energy or perhaps giving up energy in order to make the reaction happen.